Welcome to 5.8 to 5.9 integrals of inverse trig functions in the other direction, but you'll notice I only have 3 of these formulas written down. Well, if you look back at your derivatives, there are 6 formulas: arcsine, arctangent, arcsecant, and then you have arccosine, but arccosine was just the opposite of arcsine. So we don't really need both of those. Arccotangent is the opposite of arctangent. So we really don't need those 2. We just need one. And arcsecant and arccosecant just differ by a -1. So we're going to stick to the positive versions, and we're going to get everything into this form right here. So they're going to give us this guy right here. We're going to find out what u is equal to and find du, because when you find u, you always have to find du, and we're going to find out what a is equal to as well. Once we know these 3 pieces of information, we are ready to plug it into our arcsine, arctangent, and arcsecant. Now, arctangent is totally different than the others. There's no square root. So it's easy to see the arctangent because it's addition, no square root. Now for the arcsine and the arcsecant, it's kind of a little trickier. The trick is if your variable is the one that is negative, you've got arcsine. If your variable is positive, you've got arcsecant. Don't rely on this always being there, because if you remember from yesterday, we had an arcsecant and u was an exponential. The exponential canceled out, so you didn't actually see this in your answer. So don't let this be the indicator of your secant. Let this be the indicator. Okay, so you're looking at where your variable is. Is it negative? It's sine. If it's positive, it's secant. All right, so let's look at some easy examples, or easier examples, or not as stressful answers. All right, so when I'm looking at this right here, just look through them real quick and see if you can figure out which one you've got. Look at this one. You've got a square root, so I know it's not arctangent. My variable is subtraction, so I know I have arcsine, and remember that's just the inverse of sine. Here, no radicals. Here, no radicals, so we know that's an inverse tangent. Okay, so just kind of get a little bit of a picture of what you've got. So we're going to figure out what u is equal to. Well, u is your variable squared, or u squared is your variable squared. So if you were to square root that, you know u would have to be x. Well, if I took the derivative, that's going to be dx, so that's nice. And then my a, well, this is a squared, so that means a has to be 2. So when I find the inverse sine, I know inverse sine, there's nothing on the outside, there's no coefficient there, so it's just inverse sine of u divided by a, so x divided by 2. And don't forget your plus c, because this is indefinite integration. So that wasn't bad at all. I know some of you are saying, just wait. All right, so we already know what we've got here. X squared would be u squared, so that means u would just be x. Du, once again, is dx. So I have everything that I need. My a, well, a squared is 16, so a would be 4. This is inverse tangent, so we start off with 1 over a, so 1 over 4. Arctan or inverse tangent, whichever one you like better. U divided by a, so x divided by 4 plus c. Okay, now 17. 17's a little weird. This time my u, well, there's u squared, so u has to be 3x. So that means du has to be 3dx. I don't have the 3 part, so I do have to fix that. I need the 3, so I'm going to put the 3 here, and I'm going to counteract that with a 1/3 out in front. So I have my du, I have my u squared, I have my a squared. Well, if a squared is 2, then that means a has to be square root of 2. So that's kind of weird. I need to have all of those pieces there. So now if I were to substitute all of that out, I would have du divided by a squared plus u squared. So we're still going to have to be cognizant of our du. Anytime you make a substitution, you're going to have to be cognizant of that du. Well, I have that 1/3 out in front from before, and then I have my 1 over a, which is 1 over square root of 2, and then our inverse tangent of u over a, so 3x over square root of 2 plus c. Now you can go ahead and multiply your 3 through, so you have 1 over 3 square root of 2 inverse tangent. When I do my inverse tangents, I always like to put the angle in parentheses. You really don't need it, but it gets awfully crazy looking if you don't. All right. So let's do a couple more examples before. Don't look at this statement on the bottom. Ugh. All right, so let's just kind of identify what we have. On 18, we know we have an inverse sine. 19, look at this guy. Don't look at what's out in front. Your 4x squared is positive, so you have inverse secant. And then here, once again, you have your inverse secant. Okay, who's positive determines whether you're inverse sine or inverse secant. All right, so sine, looking at my u squared is 4x squared, so u is going to be 2x, which means my du has to be 2dx. I don't have the 2 there, so I'm going to put it in, plug this in, and then counteract it with the 1/2. What you have on top has to equal du. That has to be du. Until that occurs, you are not ready to integrate. So this 1/2 I have out in front is going to stay out in front. And then inverse sine of u over a. U is 2x, a is 1. Oops, we forgot to write our a. A is equal to 1. So we have 2x over 1, which is just 2x. I like to put my little parentheses in there, plus c. All right, so let's look at our next one. We know it's secant. Let's do green. So when I'm looking at that, u squared is 4x squared, so u is 2x. And then du is 2dx. I don't have my 2, so I'm going to put my 2 in there. I need that for my du. I counteract it with a 1/2, just like I've done before. Well, now remember what your inverse secant looks like. Your inverse secant is supposed to be du over u square root of u squared minus a squared. So that u, I need that u out in front. If you look, I don't have that u out in front. I have just x. So wait a minute, look, you have that 1/2 out in front. We're going to move that 1/2 back inside. So this is one of the few times we actually need that counteracting part. We need that inside. So that's kind of weird. So when I rewrite this, I have my 2dx over 2x square root of 4x squared minus 9. So that 2 that I needed for my du, that 1/2, I needed that 1/2 on the inside this time. Now, last thing I need to do is identify what a is equal to. Our a squared is 9, so a is just plain 3. So when I write out my answer, I know it is 1 over a, so 1 over 3 times arc secant, or secant to the -1 power. It's not to the -1 power, but it's inverse notation. And then the absolute value of u over a plus c. Okay, so that one was a little weird. We needed to make some alterations due to the du, and those alterations actually came in handy for my u. All right, so our last example that could be slightly pretty. I don't know what I was doing there. Sorry, kids. Let's go red. So I'm looking at that. I need u is going to be 3x. So du is going to be 3 dx. And I know a is going to be the square root of 5. So one of these we don't need. That 2, I don't need that 2 there. But that 3, I do need that 3 on the inside. So see this little 3 here? I need to multiply the top by 3, and usually I counteract with a 1/3 out in front, but I need that 3 on the inside. So 3 over 3, that's just multiplying by 1. That 2, I don't need that 2, so that 2 is coming out. But look at where that 2 is. That 2 is on the bottom, so it's going to come out as a 1/2. So I have 1/2 integral 3 dx over 3x square root of 9x squared minus 5. So I have my du over u times the square root of u squared minus a squared. So 1/2 times 1 over a, which is 1 over square root of 5, times inverse secant or arc secant, however you want to write it, it's up to you. Absolute value of u over a plus c. And once again, you can multiply that out so you don't have quite so many fractions. Okay, so these were relatively pretty. We needed a little bit extra in there for our du, but for the most part it wasn't much more difficult than what we had for our u substitutions before. So now let's do an example that might be a little creepier. Anytime you see your exponential, note that something probably had canceled. So we need to uncancel that, so to speak. First thing we're going to do is identify what we have. Anytime your variable, whenever you have a square root, you're either going to have inverse sine or inverse secant. Look at where your variable part is. Your e to the 2x, that's your variable part. Is it positive? Yes, you've got inverse secant. If it's negative, you have inverse sine. So we're going to start the process just like we know what we're doing. We've got u equals, okay, u is going to be e to the x. So that means du, the derivative of e to the x is e to the x dx. And then a, of course, is going to be 1. Now the problem with this one is that I can't just throw x's in there. I can multiply by any number and it's reciprocal because that's just multiplying by 1. I can't throw variables in there. I get into trouble. Well, what I really need is to have a du. So remember back substitution? We're going to have to back substitute again. Only this time, we're going to back substitute for our dx because I need this guy to go away. So this guy, I need to go away because I already know this is u squared, so he's going to go away and I'll have my problem all in terms of u's. So in order to solve this for dx, I'm just going to divide both sides by e to the x. Okay, so dx is going to equal du over e to the x. So I'm just going to make my little substitutions here. My dx, I'm going to substitute that out. So that's going to be du over e to the x all over my square root of e to the 2x minus 1. Well, if I put that over 1, and flip and multiply, I'm going to end up with my du over e to the x square root of e to the 2x minus 1. And remember, this is just du over u square root of u squared minus 1. So we have everything we need now. We know this is inverse secant. We know what u is equal to. We know what a is equal to. We are ready to go. okay, because we get our 1 over a, which is 1 over 1. Okay, I'll write it down even though I feel silly. We'll fix that in the next step. Inverse secant or arcsecant. The absolute value of u over a, so the absolute value of e to the x over 1 plus c. So really this is just arcsecant. E to the x is always positive, so I really don't need the absolute value, and I certainly don't need the over 1. So that would be my final answer. So when you have exponentials, know that something has probably canceled, and know that you are going to have to do a little back substitution to get that dx out of there. Now 13 isn't really so tricky, it's just the fact that x plus 2, I have 4 minus x squared. I kind of almost look like I have u substitution. If I let u equal 4 minus x squared, du would be negative 2x, so that x is helpful, but the 2 is not. So it's addition up here. So what we're going to do is we're going to split that apart. Okay, into 2 separate integrals. We're going to do green to be all festive. Okay, everybody gets a dx in their corresponding color. It's all about fashion and math. So now this in red, we can use our u substitution. So we're going to use this u substitution here. I need that negative 2 in front of my x dx there, so I'm going to put the negative 2 in, counteract that with a negative 1/2. So now this is negative 1/2 times the integral du, oopsie, I lost my square root, over square root of u, or u to the 1/2. So the red guy is ready to go. Now the green guy, he needs a little bit of work. I've got 2 over the square root of 4 minus x squared. Ooh, that's an inverse trig function. My u is going to be x. So my du is going to be just dx. My a is going to be 2. Well, I don't need that 2 here on top. So I'm going to pull him in front. So now I have everything I need for my trig function. So we're getting ready to integrate. So when I integrate, negative 1/2 times du over u to the 1/2 power. Remember, this is u to the negative 1/2, so when I add 1 to the exponent, I get 1/2. I divide by 1/2, I get negative 1 u to the 1/2 power, plus this in green is going to be 2 inverse sine or arc sine, whichever one makes you happiest, u over a, so x over 2. And then we have to have the plus c because this is an indefinite integral. Do not circle the answer because you have a u in there. You should never have a u. U is 4 minus x squared, because remember, everything in the red goes together. And then plus, you've got your 2 inverse sine of x over 2 plus c. So you could have inverse trig functions and u substitutions all in the same problem. So what you want to do, our new game plan, is look at what your integral is. Can you use a u substitution? If you can, then make that happen. If you can't do a u substitution, then you're probably left with an inverse trig function. So here's my final answer. We had a little bit of both. U sub and inverse trig function. So let's look at our last example. Holy cow, how exciting. Now we had a problem very similar to this, wow, way early in chapter 4, where it was actually a perfect square and we factored it and then just used a normal u substitution. Well, this guy doesn't factor. Okay, so this does not factor. Doesn't factor. So a U substitution is out of the mix. So that means I am looking at an inverse trig function. Doesn't factor, so no U sub. That means we've got to make a trig function happen for us. Okay, so it's got to be an inverse trig function. Which one should we shoot for? Well, we don't have a radical, so that means inverse sine and inverse secant, no longer an option, so we're going to shoot for inverse tangent, which means we need to get it looking like that guy. So we're going to have some kind of perfect square. So we're going to take the bottom here, and we're going to make a perfect square. So let me rewrite here, dx. Now remember, when we're trying to make this into a perfect square, we're completing the square. That plus 7, not helping. So we push it out of the way, and then we ask ourselves, what could we add into this little spot here to make this a perfect square? You've got a 1x squared, so you take half of the linear term and square it. So half of negative 4 is negative 2, squared is 4. So I've just added 4 to the bottom, so I also better subtract 4 from the bottom. That way the bottom has not changed in value. It has changed in look, but not in value. So now what's inside the parentheses is a perfect square. It is x minus 2 squared, and then 7 minus 4 is positive 3. So we've got our inverse trig function look. Our u is going to be played by x minus 2, so we have quite the hearty little actor there. Du could be a problem, but the derivative of x minus 2 is just dx. Woohoo! And then a is going to be, 3 is a squared, so a is going to be the square root of 3. Now that we have all the parts, inverse tangent is 1 over a times the inverse tangent of u divided by a plus c. Okay, so look at your problem. If you can do a u substitution, then by all means do a u substitution. But if what you want to let u be, there's no du you can make happen, because remember, you can only multiply by a number, counteract that with the reciprocal. You can't multiply by x. That's the problem here. If u was going to be the bottom, du would have to be 2x minus 4, and I cannot generate that x. So that's what failed in our u substitution. I can't come up with x's. I can only come up with numbers. I can only multiply. So u substitution was out, so inverse trig function, I had to make that happen. Since there weren't any square roots in here, I only had one choice, and that was inverse tangent. Alrighty, I'll see you in class tomorrow.